Welcome back to the deep dive. We're continuing our journey through the OEIS, especially for you number theory students out there. Today we've got a really interesting one, LA000343.
Ah, yes, a classic.
It's got this dual identity, hasn't it? Algebraically, it's just the fifth power of the generating function for rooted trees, b of x to the fifth.
That's the BX, yes.
But then combinatorially, it counts something quite different or seemingly different. Linear forests made of exactly 5 rooted trees. The numbers themselves, starting at n equals 5, they go 1, 5, 20, 70, 237, 21. Keeps going, obviously.
Right. And our job today really is to bridge that gap. How does this algebraic thing, taking a power series to the fifth, relate to this, specific kind of graph structure? How do they end up counting the exact same thing? That's the puzzle.
Okay, so let's maybe start with the basics, the building blocks, trees and forests.
Good idea. So from graph theory, a tree is basically a connected graph, but with no cycles, no loops, any 2 points, exactly one path between them.
Simple enough.
And a forest is, well, just a collection of trees that aren't connected to each other, a disjoint union, we'd say.
Got it.
And then there's the rooted tree, which is just a tree where we've picked one special node, one vertex, and called it the root. Gives it a direction, sort of.
Okay, now for the tricky part in the second definition of A000343, the linear forest. That sounds specific.
It is very specific. A linear forest means every piece, every connected component in your forest has to be a simple path graph.
Yeah.
Like beads on a string.
No branching off.
Exactly, no branching. It has to be a cyclic, like any forest, but it also needs to be what we call claw-free.
Claw-free.
It's a technical term. It just means you can't have a central vertex connected to 3 or more other vertices that aren't connected to each other, like a star shape. That's forbidden.
Ah, okay.
So another way to think about it is that every single vertex in a linear forest can only have degree 0 isolated, 1 an endpoint, or 2 in the middle of a path, nothing higher.
Right, that enforces the line idea. Okay, but wait, here's something I'm wondering about.
Well,
The other definition uses bx, the generating function for all unlabeled rooted trees, right? Sequence A000081.
that's correct. BX counts all of them.
But general rooted trees can be super branchy. They can have vertices with degree 3, 4, whatever. They definitely aren't always paths. So how can bx to the fifth power count these very restrictive linear forests? Shouldn't it be counting combinations of any 5 rooted trees, including the bushy ones?
Ah, that is precisely the crux of it. You've hit the nail on the head. It seems like a contradiction, doesn't it?
It does a bit, yeah, like an overcount.
So BX does count all rooted trees, and BX to the fifth does algebraically represent combining 5 independent disjoint structures, each counted by BX. The magic happens because of a known, let's call it a deep combinatorial equivalence. When you're dealing with partitioning and vertices into exactly unlabeled rooted components, there's this surprising result. It turns out that the number of ways to do this using any k-rooted trees is exactly the same as the number of ways to do it using k-rooted path graphs, which forms a linear forest.
Really? That specific equivalence holds.
Yes. It's not immediately obvious, but it's a proven result in enumerative combinatorics. The constraints involved when partitioning into exactly 5 components and doing it unlabeled force the count to match the linear forest scenario.
Wow. Okay.
So the generating function machinery, bx to the fifth, automatically handles this. The exponent 5 tells the generating function, combine exactly 5 independent things counted by bx.
And the underlying math ensures that this count just happens to equal the count for those specific linear forests of 5 paths.
Precisely. The algebra doesn't need to know about the path restriction explicitly. The structure of the problem makes it work out.
So let's try and synthesize this for everyone listening. The coefficients in the power series for bx raised to the fifth power.
Let's call them an.
Right, an. This number counts the ways to use n vertices to build something that falls apart into exactly 5 separate disjoint pieces. The algebra, the b base 5 part, guarantees there are 5 pieces and that each piece is fundamentally related to a rooted tree structure. And then this deeper combinatorial fact tells us that this count is numerically identical to counting the ways to form a linear forest with 5 rooted paths using n's vertices.
You got it. It connects the algebraic operation directly to the graph structure count.
It's quite elegant, really.
It is. And, this sequence isn't just some obscure thing. It appears in foundational texts like Riordan's work, Sloane's original handbook. It's been studied for a while.
So the aha moment here is seeing how A000343 neatly ties together these graph properties, needing 5 components, being acyclic, being composed only of paths with the sheer power of generating functions. Just take the series for rooted trees and raise it to the fifth.
A beautiful demonstration, yes.
Okay, let's leave our listeners with something to think about. We've seen that bx to the fifth power counts these linear forests of 5 rooted trees. So what about the simpler case? What specific kind of graph structure do you think would be counted by the square of the rooted tree enumerator, bx squared? What does that correspond to?